three gates we saw. We saw AND gate, OR gate, and NOT gate. And then we also introduced what is an universal gate, though we have not seen really the applications of universal gates. We just said that any implementation is possible using the universal gates, which means using NAND, NOR, and NOT. In fact, you can skip the NOT also just with NAND and NOR. Now, let us see the real applications of NAND slowly. But before that, first let us evolve some of the concepts based on these NAND gates. Say for example, what we are going to see today is a bubbled NAND gate. This bubbled NAND gate is equivalent to something, right? I'll tell you what is that is equivalent to. But there is a meaning to this bubbled NAND gate. What is a bubbled NAND gate is? I'll come back to this bubbled NAND gate later. Before that, let us first have an AND gate now, as mentioned here. Let us first have an AND gate. AND gate will have one input. Obviously, this is going to have two inputs, right? So it will have two inputs. So this is an AND gate. Now, instead of giving positive input A and B, what we'll do is we will give a complemented input to the AND gate, meaning let us NOT this. So when you NOT this, what will happen? A becomes A bar here, and similarly B becomes B bar. My objective is what? My objective is to give a complemented input to the AND gate. So what will be the output of this? The output of this AND gate is going to be A bar dot B bar, similar to A dot B, right? If we give an uncomplemented input as A and B, then the output of an AND gate is A dot B. If you give a complemented input A bar and B bar, then the output is A bar dot B bar. Instead of completely drawing as an inverter and then an AND gate, the whole circuit here, which has been marked here, this circuit is equivalent to, you can just put a bubble here, right? Meaning both the circuits are equivalent. Both the circuits are equivalent here, meaning that you are bubbling your inputs. That is why it is called this kind of if you have bubble at the input side, then we call it as a bubbled AND gate. This gate is called as a bubbled AND gate. What is that we are really doing? We are inverting our inputs and then we are giving it to the gate. So here also, this output also, it is A bar dot B bar only. Now, what is our NAND gate? NAND gate means you have a AND gate and then you complement its output, right? If Z is your output of your AND gate, if you pass this through an inverter, the output here will be Z bar. So in short, we have just saw in the last class itself, this inverter can be just simply drawn as a bubble here. Okay, and this becomes a NAND gate. So here also it is also the same condition here. You are having an AND gate here. This is nothing but your AND gate. This AND gate, you pass the output of this AND gate, you pass it on through a bubble, or you invert this output. Now, if you invert this output, what will happen? Your output here is A bar dot B bar. Now, when you pass it on to an inverter, again the whole output here will be bar or complemented. So your output here is A bar dot B bar, the whole bar. Now let's do one thing. Please remember this expression. Your expression here is A bar dot. Okay. Your expression here is Z is A bar dot B bar, the whole bar. This is what is the expression we have, right? A bar dot B bar, the whole bar. Now, okay, I have written x here. Let us write it as a. Let us write it as b, and let this be z. Uh, okay, let me not use this particular table because I have to write for a bar dot b bar also. So I'm just moving down slight a bit. Yes. Okay. Now let me write a new truth table. Okay. It is A, B, right? So if it is so, and my output is going to be Z. Okay. Now I don't want A, but I want A bar. So what shall I do? Let me write A bar here and then B bar here and then my Z output. Okay. So normally my inputs will be 0, 0, 0, 1, 1, 0 and 1, 1. For a 2-bit combination, this is what is the combination I will have. Now, what is complement of 0? It is 1. What is complement of 0 here? It is 1. Complement of 0 is 1. Complement of 1 is 0. Complement of 1 is 0. Complement of 0 is 1. 1 and 1 becomes 0 and 0. Right? Now, what is the AND operation of this complement? Now, I should write the AND operation, that is A bar dot B bar's output. What is 1.1? 1.1 is 1. 1.0 is 0. 0.1 is 0. 0.0 is 0. But still, this is not I want, but I want A bar dot B bar the whole bar. So it is A bar dot B bar, which is this column. I have to complement the whole output of this. So what is complement of 1? This is 0, 1, 1 and 1. Now compare your input and your output. What is your input here? Your input here corresponds to this one, right? This is what A and B are your inputs. And what is your output? A bar dot B bar, the whole bar is your output. Let us compare this one. 0, 0, this is output is 0. 0, 1, your output is 1. 1, 0, your output is 1. And 1, 1, its output is 1. What is that you should recall? You have already seen this particular truth table already. What is this equivalent to? This shaded is equivalent to, this is nothing but an OR gate output, right? So let us look at the, so which means that a, a bubbled, I have bubbled my input, a bubbled NAND gate is equivalent to an OR gate, right? Now this, and what is the Boolean expression for an OR gate? Boolean expression for OR gate is A plus B, whereas a Boolean expression for a bubbled NAND gate is A bar dot B bar, the whole bar. Which means that what is that we conclude from here is this A bar dot B bar, the whole bar, okay, my system, I think it's getting hacked. Okay, this A bar dot B bar, the whole bar is equivalent to A plus B. How is it possible? Yes, it is possible. This is applicable by a rule called as De Morgan's law. You must have heard this particular term, but let me introduce here. This is called as De Morgan's law. How are they equivalent? How are they equivalent is, there is a rule that I am going to tell you, which is change the sign and break the line. I think it is break the line and change the sign. Okay. Now, what is that break the line and change the sign? What is the expression we saw? We saw A bar dot B bar, the whole bar, right? Now, if you break the line, what is the line that I am going to make? I am going to break. This is the line I am going to break. If I break this line, I have to change this particular sign. I hope now I have made it clear. So let me break the line. If I break the line, what will happen? I am having A bar already and I have breaked the line this bar, double bar, this long bar now has been broken into two small bars across the variables here. I have broken the line. Then what should I do? I must change the sign here. This dot now will become plus. Now what is a double bar equal to a complement of a complement is nothing but a only, right? So now this becomes a plus b, right? So this particular law is called as the De Morgan's law, and yeah, and the rule that I'm going to introduce here, I think it got hanged. Yeah, okay. Yes, which means that a bar dot b bar, the whole bar, is equivalent to a plus b. You will apply the rule, break the line and change the sign, which is what I said you. This is bubbled NAND gate. Similarly, let us see bubbled OR gate. Okay, so I'll come back to this particular part later. Now bubbled OR gate. What is a bubbled OR gate is? I am going to bubble the inputs of my OR gate. This is my OR gate. This is my OR gate. I am going to bubble its input. Normally it is A and B. If I bubble its input, then A and B becomes A bar and B bar. I have created a NOT gate here. So what will be my output? Ideally, output of a OR gate is A plus B. Now, since I have bubbled my inputs are already A bar and B bar. So the output of an OR gate is A bar plus B bar. So the whole circuit here, this whole circuit, this can be simplified, or this is equivalent to a bubbled input. That is, you can just create a bubble across your input and then your OR gate. What is our objective here? We need bubbled NOR gate expression. Okay. Now, what we'll do is, this is what is equivalent to. Now, if you bubble this in the sense, if you pass this part of the circuit further through a NOT gate, then what will happen? This A bar plus B bar will be further complemented once more. So the output at this particular point here will be A bar plus B bar, the whole bar. Now what is this A bar plus B bar, the whole bar equivalent to? If you do the similar analysis what we did here, you will see that they are equivalent to AND gate. Maybe quickly we will do A input, B input, okay. So this is 0, 0, 0, 1, 1, 0 and 1, 1. What is that we want? A bar we want and B bar we want. So the complement will become 1, 1, 1, 0, 0, 1 and 0, 0. And what is that we want? We want A bar plus B bar. We want A bar plus B bar, the whole bar also. So first we need A bar plus B bar. This is what we need. And later we need A bar plus B bar, the whole bar. So what is A bar plus B bar? That is, any 1 is 1, your output will be 1. So here I am having 1, so output is 1. Here I am having 1, output is 1. Here I don't have 1, so the output is 0. And the complement of this column, is this one. So 1 becomes 0, 0, 0 and 1. What is this equivalent to? This is equivalent to your AND gate, right? So there is an application based on this. That is why we are looking at this. Hence, this circuit here is equivalent to AND gate here. Any doubt? Yeah. Again, the rule applies the same. Break the line and change the sign. What is that? Break the line and change the sign. The expression that we have here is A bar plus B bar, the whole bar. I will break the line and change the sign. So if I break the line, this whole bar become one single bar and B bar, and the sign gets changed, plus gets changed to dot. right? And what is A double bar? A double bar is nothing but just A dot B. Okay. So, which means that a bubbled NAND gate is equivalent to an OR gate. A bubbled NAND gate is equivalent to a OR gate. Okay. Again, I repeat in case I misspelled. A bubbled NOR gate is equivalent to an AND gate. A bubbled NAND gate is equivalent to an OR gate. Now, before moving further, using these NAND and NORs as inverter, we will come back slightly later. But before that, is it okay? Yeah, okay, we will complete this and then we will go back. Okay. Now, we know we started slowly understanding the power of the NAND gates and NOR gates. Now, an inverter also, you can use NAND gate and NOR gate as an inverter. What do you mean by an inverter? Inverter is nothing but the NOT gate, right? Anything that inverts, anything that complements is called as an inverter. The other name, just we saw that it is NOT gate. Now, if you look at the NAND gates truth table, what is, if you recall the output of a NAND gates truth table, NAND gates truth table is A, B, and A dot B, the whole bar, right? So this is what is the NAND gates truth table is. So 0, 0, 0, 1, 1, 0, and 1, 1. The output will be whenever anything is 0, then you will have an output of 1, right? So complemented form. So here again it is 1, 1, and 0. This is what is the output of a NAND gate is. Now, if you want to use a NAND gate as an inverter, if you make a connection something like this, that is, if both the inputs are same to a NAND gate, then you will get a complemented output. Let us look at the truth table here. Look at the truth table here. When both the inputs are same, these are the two places when both the inputs are same. But the output that you are getting is a complemented form of your input. When both the inputs are 0, your output is 1. When both the inputs are 1, your output is 0. So, which means that creating a connection, something like this, will create a complemented output here. Right? So, an AND gate, when you create a connection, something like this, then it will actually act as an inverter. Similarly, for a NOR gate also. NOR gate also, the true, if you create a truth table for a NOR gate, again, A dot, okay, let me write here so that I save some time. A plus B, the whole bar, right? Now, when both the inputs are 1, then you will get output 1 for an OR gate and then its complement. So, this output is going to be 1 and 1 will be, sorry, 0 and 0, 0 complement 1, 0 and 1, 1 complement 0, 1 and 0, 1 complement 0, 1 and 1, 1 complement 0. Now again, you look here, when both the inputs are same, you are getting a complemented output. When both the inputs are 1, your output is 0, right? So hence, you can also use NOR gate also. You can also use NOR gate also as an inverter circuit. Now let us look at some more example, say some more example in the sense, what we are going to do here is, instead of having a connection like this, let us give always one input to one of the terminal and A input as the other terminal. Here, so what will happen? If I am giving one input to one terminal, so what are the cases here? I have to draw it again. I have to write the truth table again. Never mind. So my input is A, B, and my NAND gate output, A dot B, the whole bar. So one input is always 1, right? So let my B input is always 1. Only one possibility. Two possibilities are possible, right? One input may be A and other input may be A bar, right? I've just changed it to a variable instead of 0 and 1. So you compare this particular table, both are same. When is B1? B is 1 here and B is 1 here. And A here, at one time it is 0 and other time it is B. So which means I can write this as A bar, and I can write this as A. Okay. So both are same. So this is in a generalized way. Now look at, compare the truth table. Now for a NAND gate, your output here is 1, right? When it is A and 1, your output is 0. When it is A bar and 1, your output is 1. So when it is A and 1, your output is 0 here. And for A bar and 1, your output is 1. Which means that when it is A, you are getting A bar as an output. When it is A bar here, you are getting A as an output. Right. So this is called as we call as a controlled inverter. Similarly, for an OR gate operation, when your one input is 0, and if your other input is A, then you get your output as A bar. So similarly, you can verify with this truth table. Okay. So what we saw in these two examples are these. If you connect, if you give one input as 1 and other input as A to an AND gate, it will invert your output. Similarly, if you want to invert an output with just one input, then you use an OR gate, but you provide the other input as 0. Please note, 1 means what? You will provide this 1 as a high voltage. Say for example, you will provide plus 5 volts. If it is 0, what does it mean is you will provide this input, you will short this input to ground. This is what it means. Okay, we have seen multiple gates here, AND, OR, NOT. Now let's look at XOR gate. What is an XOR gate is, the symbol for an XOR gate is, you make a plus and then a circle inside, outside. This is the symbol for an XOR gate. And what is the circuit symbol? The gate symbol is, it is an OR, but it is XOR, right? So you will create some space between and then you will create an OR. So the XOR gate, what is the truth table is, whenever both the inputs are same, then you will have an output 0. You see here, when both the inputs are same, you will have an output 0. When both the inputs are different, then you will have output 1. Right? So this is a very, very important property. You will use this very often. Okay. Even till the last unit of this chapter, you will use this particular property of XOR gate. Now, another property of XOR gate is, if any of your input is 1, okay, so let us assume that B is the input 1 here. So where do you have B as 1? You have B as 1 here and B as 1 here. And here A value is 0, which means A bar, and A value is 1, which means A. Now look at the output here. A bar is still A here, 1. So A bar becomes A, and 1 here, A becomes A bar here. Meaning, if you want to use an XOR gate as an inverter, like the previous cases, these two cases, that is NAND and NOR cases, if you want to use XOR gate as an inverter gate, then it is similar to NAND gate, that is you give one input as 1 and other input as A. Then if it is A, then it is A bar. That is the only difference. Your output will become A bar now. Okay. So this you must remember. Now let's do some play around with XOR gate. I'll have to slightly go back. Yeah. Now, so far we have seen different possible combinations of gate implementation, right? You know that we have already implemented some gates using AND, OR and an inverter, AND, OR and a NOT gate. We have seen that. Similarly, you can have different universal combinations. That is, any circuit can be implemented using a combination of XOR and AND gate. Similarly, there are 4 different possible combinations. One is using AND, OR and NOT gate. Second is using XOR and AND gate. Third is using XOR and OR gate. And fourth using only NAND gates or using only NOR gates. These implementations are universal implementations. So that is why you must know the property of XOR gate in detail. So we have already seen this one in very detail, and this we will be seeing it later. Let us just touch upon the use of XOR plus AND gate possibility. Say, for example, you want to implement A plus B implementation. This is nothing but, what is this implementation A plus B? This is nothing but an OR gate implementation. What is OR gate equivalent to? Let us break the line and change the line by applying De Morgan's law. It is A bar dot B bar, the whole bar expression. I can implement this expression using just the XOR gate and AND gate. How is that I can implement? First, how can I draw A bar now? Using XOR gate, if I want to create an A bar here, then one input will be 1 and other input is A. Then my output here is going to be A bar. Then I will create B bar. How can I create B bar? Again, one input is 1 and other input is B. And then if this is an XOR, this output will be B bar. Now what have I done? I have created A bar and dot B bar, A bar and B bar I have created. I have to use a combination of XOR and AND gate. So if I add these two operations, what will be its output? This output will be A bar dot B bar here. Now what is that I need? I need the whole bar. If I need the whole bar, I should use, please note, I should use only XOR only. So this input and another input with 1 as a high always, I will use one more XOR. Here this will act as a complement of this line. So what is the complement of that line? Which is nothing but A bar dot B bar, the whole bar, which is nothing but an OR implementation. It means that OR gate can be implemented using XOR and AND gate. Similarly, you can use XOR gate and OR gate also. Let me clear this out. Similarly, you can use XOR and OR to implement any circuit you want. How do you implement an OR gate, same OR gate implementation, right? So you know that A plus B can be written as A bar dot B bar, the whole bar, right? This can further be written as you create one more bar of, or you break the line. Okay, so A bar dot, no, I think that's it. This should be A dot B. Okay, I'm sorry. Yeah, this should be A dot B, which means that we are trying to implement. Yeah, all right, I'll explain. So if you want to implement AND gate, okay, this AND gate can be written as double bar, right? Complement of a complement is the same. You know, break the line, change the sign, right? Do the same thing, break the inner line. If you break the inner line, then it becomes A bar, change the sign, this becomes B bar, and then the bar remains the same. This can be implemented using XOR and OR gate. How? This particular part is nothing but A bar implementation using XOR. Similarly, this particular part is B bar implementation using XOR. You combine this output here through an OR gate, because you can implement using XOR and OR implementation, and the output here will be A bar plus B bar. You want to do this inversion again, so you pass it on through one more XOR gate with one as other input as high, so it becomes A bar plus B bar, the whole bar. Okay, so what does this mean is XOR is such a powerful gate which can be used for any possible combinations of circuit implementation. And one more powerful feature of XOR gate is this not equality function. Right? XOR, it has got a not equal function. What is this not equal function is? From the truth table only. If our inputs are A, B and A XOR B is our output, you know that when both the inputs are different, this is 0, this is 1, this is 1 and this is 0, your output will be 1 for that, right? So rest of the output, did I do the same thing? Just a minute. Yeah. Yeah. So when both the inputs are same, your output will be 0. So this not equal to function is a very powerful function. Okay. So let us see how it is a powerful function. The other form of writing an XOR is you can also write XOR function of x comma y. Since we are looking at an XOR function, this can be written as XOR of x comma y, is where XOR is a function, which can be written as x XOR y using circuit symbol. Or in terms of the Boolean expression or Boolean algebra, this x XOR y can be written as x bar y plus x y bar, or a XOR b can be written as a bar b plus a b bar. Okay, so this is also equivalent to XOR gate only. Now let us look at certain identities of XOR. 0 XOR with x will always be x. Look at the truth table. Where is 0? Let us assume that b is 0 here, right? So this is here, it is 0, it is 0. When a is a bar, your output is also a bar. When a is a, your output is also a. So which means that x XOR 0 is x, x XOR 1. You look at these inputs here. These inputs, they are complemented form. So x XOR 1 is a complemented output. When both the inputs are same, x XOR x, 0. When x XOR complement 0 and 1, your output is 1. And certain properties of XOR gates are x XOR y is equivalent to y XOR x, or similarly for 3 inputs, x XOR y XOR z is equivalent to x XOR y XOR z. And you know that XOR, just we saw that XOR y is equivalent to x bar y plus x y bar. When you implement this, you look at the AOI implementation. We call this as AOI implementation. What is this AOI implementation is? And or inverter implementation. So x bar can be written as, so this is your x, so here it is x. Here you pass it, the same input you pass it on through a NOT gate, it becomes x bar. Okay. So x bar, I think, yeah, no. Actually, this input here will be, there seems to be a mistake. One input here will go here actually, so okay, so this is, if this is x, one input will go here and this inverter input will go here where this is y. Okay, I think I will draw it maybe here. This is x, this is y. Okay, so what you need x bar, so you need x bar, you need y bar. Okay, and x bar y, right? If this is y, okay, we already have y here, so this y, this to be ANDed. Similarly, this x and this y bar ANDed and ORed. This will be your, what is this expression here? This expression is x bar y plus x y bar. Look at the number of gates you are using. You are using 1 gate, 2 gate, 3, 4 and 5 gates you are using, right? So if you implement the same XOR gate using NAND gates, you can reduce the number of gates. Instead, if you are using XOR gate, we normally don't use XOR gate because it's slightly costlier, and at the same time, certain logics might require more number of gates than expected using XOR gate. That is the reason we stick with the NAND gate and NOR gates. The other gate which is of slight importance is an XNOR gate. What is an XNOR gate? XNOR gate is also called as an equality function. Whereas your XOR gate is a not equal function. What does this mean? The complement of XOR gate is what is your XNOR gate is, meaning that when both the inputs are 0, when both the inputs are equal, your outputs across an XNOR gate will be 1. The output of an XNOR gate will be 1, and when the outputs are unequal, when the inputs are unequal, your output will be 0. That is why XNOR gate is called as an equality function. And the expression is given as AB plus AB bar, or in terms of X and Y, it is XY plus X bar Y bar is called as your AB bar is missing. X bar Y bar is your XNOR function. Okay, so just a simple simplification for that is given. Did I do it for XOR? No. Okay, so a simple we'll come back to this part later because we will do it for XOR gate and then we will do it for XNOR, then you will understand. So this XOR gate, it is called as an odd function. Why it is called as an odd function is, you know that X XOR Y is given as X bar Y plus X Y bar. If in case you have 3 inputs, then they are given as X Y bar Z plus X Y Z bar, X bar Y bar Z plus X Y Z. Similarly, in case you have 4 inputs, then this is how the XOR expression is given. And how do you remember this is, first one, that is if 3 variables are here, that is X, Y and Z. X here is 1, Y bar and Z bar, they are 0, 0. Similarly, X bar will be 0 and Y will be 1 and Z bar is 0. X, Y bar, here only Z will be 1, rest all will be 0. And the last expression, everything will be 1. Similarly, you must be able to do, if I ask you what is an XOR function of X, Y, Z, A, B and C. If I ask you to do the XOR operation of these and get the expression, you must be able to do this, right? So here also I am having 4 different variables here, 4 different variables. Here you see only W will come as 1 here. Here X has come as 1, here Y has come as 1, here Z has come as 1. Now, one combination is done. Then you will have 3 combinations. That is WXYZ will come as 1, then WYZ will come as 1, then XYZ will come as 1, and WXZ will come as 1. So, in all these combinations you see that the variables come as an odd number only, right? So, observing above, you will see that odd number of one function is present in each term. Hence, this XOR is called as an odd function, right? So then if you have X, Y, Z, A, B, C, you must be able to create so many number of terms, right? So without teaching, I hope you will be able to do at least for 5 variables, you must be able to do X, Y, Z, A is already done, or W is already done. So A comma B, you must be able to write the XOR equivalent expression. Okay. So any doubt till this? Okay. Oh, we have already seen this bubble down. Now,
What
yeah.
is the
Please go.
significance that XOR is an odd function?
Yeah. In certain cases, you might, while you are performing addition for say 6-bit variable or 8-bit variables, then this odd function will be very useful in categorizing the additive terms. See, when you are adding a 6-bit addition, say for example 1 0 1 1 0 1 0, how many bits are there? 7 bits. Okay, let us take 7 bits, and if you are adding some other number 1 1 0 1 0, some number like this, then though this is physically easy, you can add 0 plus 1 is 1, 1 plus 0 is 1, likewise, but computer, they requires some block called as full adders and half adders, right? They require modules such as full adders and half adders. In that particular case, when there is a carry, then accordingly there must be some kind of a modulation here. So in those circumstances, these odd functions of XOR gate will be very useful. We will see the applications of the odd function when we perform these kind of additions, but that require slight basic concepts on theorems. We will complete this, and then when we design an adder, then you will understand where these odd functions are really used. Okay. So I think we will wind up here, because next what we need to see is Boolean algebra postulates. Slightly theoretical, it will look theory and slightly boring also. Once we complete that, then the course will be really interesting once we start with Boolean functions.